Doing well? Doing well? Okay, so the plan for today is just to continue what we started last week, structural idealization. So today I just want to show you how can we obtain the shear flows in an idealized structure with the booms and the skins. And then we are going to do one or two examples, open sections, and if we have time, closed cross sections as well. Next week we will continue with this, maybe one or two more weeks, to do more examples and detail very well this transverse shear, make comparison with the full effective and the idealized structures for different examples. And then after that we are going to talk about fatigue and fracture a little bit, not too much in detail, but anyway, at least some important concepts we need to discuss. And after that we will talk a little bit about air elasticity. So this is the program for this aircraft structures bit. One more thing, I uploaded today some notes on torsion in Blackboard, and I will upload soon also these aircraft structures, idealized structures as well. But the torsion you have already available in Blackboard. You can see what I uploaded in Blackboard. Okay. All right. So last week we learned how to, for example, if we have, I don't know if you remember, if we have a thin wall structure like this plate, we learned how to build an equivalent idealized structure where we have a plate with zero skin, and then we include what we call these booms, right? And then in this original structure, I told you that the kind of stresses that we have generally in this structure are the direct stresses, sigma, and shear stresses, tau, right? These kind of thin-walled structures or real structures, they carry these two kinds of stresses. And in our case, for the idealized structure, we said that the skin, which we assumed to be thickness equal to 0, only carries the shear stresses, right? We can say something like this. Only carries the shear stresses, tau, okay? And these booms, they carry the direct stresses, sigma, right? So if this is boom 1 and this is boom 2, this carries sigma 2, this carries sigma 1. So that was one assumption we made for the stresses that these two structures carry. So this is the real structure. This is the idealized, okay? So we made the assumption on the stresses the idealized structure carry, and we also made some idealizations on geometry, right? So we transformed this into very simple geometry, these booms, which are basically these rod elements with circular cross-section. And then last week we learned how to obtain the areas of the booms. For example, if this boom 1, this will have an area B1, this boom 2 will have an area B2. We derived last week that the area of boom B1 is going to be the width times the thickness over 6. times 2 plus the stress sigma 2 over sigma 1, where this width is this B is this is the B, and the thickness T is the thickness of this real structure, right? So this is the thickness. Okay? Ooh. And then, because we know these direct stresses, they come from bending, we also said that this can be converted in something like this, where this y2 over y1 is the distance to neutral axis. So basically, if we have a cross section like this, if we have two booms here, okay, if this is my boom 1, this is my boom number 2, we have the neutral axis here. So basically, this is going to be the distance W1 to neutral axis. This is going to be the distance Y2 to neutral axis, right? And these are the distances we need to include in this equation. And then if we do that way, we obtain the area of boom 1. If you want the area of boom 2, you just need to say B2 is equal to BT over 6, 2 plus the distance of boom 1 to neutral axis over the distance of boom 2 to neutral axis, and then you get the area of boom number 2. Okay? So we did this last week. This is just a very quick summary. What I want to do with you today is to see how the shear flows in this idealized structure. So what we are going to do now is we are going to consider, for example, two skins, something like this. And then we are going to consider that we have one boom here. Okay. We will have another boom here. And we will have another boom here. All right. So basically, we will have this skin that I will going to say this is going to be skin R minus 1. This is going to be skin R. Okay? So we have to start numbering the skins and the booms. I can say that this is going to be my boom R minus 1. This is going to be my boom R, BR. So BR is the area of this boom in the middle. And this is going to be my boom BR plus 1. Okay? And what is going to happen is we will have this shear flow in this skin R minus 1. I'm going to call this shear flow Q R minus 1. And then when I cross this boom R in the middle, my shear flow is going to be changed, is going to be different. And I will call that other shear flow QR, which is the shear flow in my skin R. Okay? So that's basically what is going to happen. If I try to draw here the shear flow QR minus 1, what I can say is that it will be in this skin R minus 1, my shear flow is going to be constant and equal to QR minus 1. But when I cross this boom R, my shear flow in my skin R is going to be different because I cross the boom. So still constant in skin R, but when I cross the boom, when I go from skin R minus 1 to skin R, I have to cross that boom in the middle. And then by crossing the boom, there is going to be a variation in the shear flow. So QR is going to be different from QR minus 1. But the good news is that in the skin, for example, if you are looking at skin R minus 1 or skin R, in any of these skins, the shear flow in the skin is constant in the idealized structure. Before, 2 or 3 weeks ago, when we studied the shear flow in the real thin-walled structures, we saw that the shear flow is not constant, right? It's linear or quadratic. Remember, in this case, the shear flow in the skin is constant. Only when we cross a boom, there is a variation in the shear flow. But then, in that following skin, the shear flow remains constant, right? So basically what I'm saying is QR minus 1 is constant in skin R minus 1. QR is constant in skin R, but QR is different from QR minus 1, right? Because I cross the boom. Okay, so that is one advantage of these idealized structures. We have constant shear flows in the skins. The only thing we need to basically derive now or calculate is what happens to the shear flow when I cross the boom. And that's what I propose to do with you now, to study that. Before we do that, I need to just show you that these booms, they carry direct stresses, right? I told you that, right? So we will have here direct stress. So if I say if I have here a coordinate system, so let's say if this is my z direction, if this is my local s direction, I can say then that this direct stress here is going to be my sigma z stress. And then in this part, I'm going to have my sigma z plus something more, delta sigma z. This is because, why do we have this? Because you remember when we studied the beam deflection, right? Imagine I have a distributed load like this in my beam. If I look at these two different sections of my beam, here I will have a bending moment in this section, and in this section I will have the previous bending moment plus a variation in bending moment because my loading is changing, right? So this variation in the bending moment will, of course, the result of this bending moment is my bending stress, which is equal to this, right? In this case, my bending stress is going to be equal to this previous one. So let's say this is my bending stress, R minus 1. My sigma R is going to be equal to sigma R minus 1 plus something more, which is due to my bending moment that is changing, right? So basically, this is my delta sigma variation in my direct stress. This happens because I'm analyzing different sections of my beam, right? So the same thing is happening here. So when I go from this section to this section, there is a variation in the bending moment. And because of that variation in the bending moment, I will have a variation on the direct stress. Okay? So I can write something like this, and what I'm going to do now is I'm going to study the equilibrium of this. I'm going to put here in green. I'm going to study the equilibrium of this boom in the middle. Don't forget, I want my goal, my aim is to calculate the variation in the shear flow when I cross the boom. So, if I study the equilibrium of this boom in the middle, I will be able to calculate that variation in the shear flow, okay? That's what I'm going to do, yes?
That must be sigma z at the top.
Yeah. This is a Z. It looks like an X, right?
Yeah.
Sorry. This is supposed to be a Z. This is sigma Z. Okay? Is okay? So let's see what... So in order to study the equilibrium of this boom in the middle, what I'm going to do is I'm going to isolate this boom and represent all the... It's always like this, right? Represent all the forces we have there. I'm going to do, if you want, the free body diagram of that boom in the middle and see what is going on in the boom. All right, so I'm going to draw the boom here. Okay? And now I'm going to represent all the stresses I have in the boom. So, first I have the direct stresses, right? If you look at here, I have this sigma z here and this sigma z plus delta sigma z, right? So I'm going to add these two first in my boom. So here I have sigma z, and here I will have sigma z plus delta sigma z. All right? So the direct stresses due to the bending, the booms, they carry that direct stresses. That's what I have. But now there is another thing that I have that is basically connected to this boom, which are the skins, right? Skin R minus 1 and skin R. So I'm going to draw them here a bit smaller. So this is my skin R minus 1. And here I will have my skin R. Okay? These skins, they are connected to this boom in the middle. And what I have in these skins, as you can see here, skin R minus 1, I will have this shear flow that I'm going to represent here. This is QR minus 1. And then this shear flow basically comes from a shear stress, right? Shear stress is the force per unit area. Shear flow is force per unit length. And we know shear stresses, they need to have this kind of distribution, right? You all agree with me? You know this from solid body mechanics from year 2, right? So this is what is happening in the skin R minus 1. And what is happening in skin R? Well, I have this QR in this direction, so I need to do the same here. So I'm going to include here in my skin QR in this direction, and then I need to have this distribution for my shear stresses, right? You agree with me? And now we will have to focus on these two, on this shear stress here and this shear stress here. They represent what? They represent the shear stress that the boom is inducing on the panels, on the skins, right? So what is going to happen is the skins, they are going to react into the booms. This is the action-reaction, Newton's third law, right? The skins are going to react into the boom with the same stresses but in the opposite direction. So I can then say that I will have here on this side of my boom, I will have, so this is QR minus 1, this is going to be QR minus 1, right? And this is QR, and I will need to have here in this direction also QR. Can you... Sorry, this writing on the iPad sometimes can be a little bit strange. I try to improve a little bit more. So this is QR minus 1. This can be a bit better. QR here. Right? Did you understand what I did here? So a quick summary again. So this shear stress is the shear that the boom is doing on the skin. So the skin will react on the boom by applying the same shear stress, same value or same intensity, but in the opposite direction. Action-reaction, right? Newton's third law. And you do the same for the other skin on the left side. And then you get now your boom, this one. with all the forces we have there. And then we just need now to write the equilibrium of this boom, okay? That's what I'm going to do. So basically what I'm going to do now is I'm going to copy. Let's see if I can do it. I'm going to copy this bit here. Yeah. So we have our boom here with all the stresses, the shear flow, and the direct stresses applied on the boom. So this is our free body diagram now. And I'm going. There's one more thing I need to include, which is this dimension here from here to here. Let's consider this infinitesimal length delta z in the z direction, okay? Yes. And now what I can do now is I'm going to say, so don't forget that this is my z direction, right? This is my z direction. What I'm going to do now is I'm going to say summation of forces in my z direction need to be equal to 0 is the equilibrium equation. Right? And I just need now to include all the forces in this z direction. So let's continue here. Which forces do I have in the z direction? Starting with the direct stresses. So I have this stress sigma z plus delta sigma z. So this is a stress. I need to have a force. So I need to multiply this stress by the area of the boom, which, if you remember from this initial slide here, the area of my boom is this BR, right? So let's say this is BR is the area of my boom. So I need to multiply this. If I multiply this by BR, I will have a force at the end. This is the contribution of this direct stress. Now I have this other direct stress in the opposite direction to the z coordinate axis. So because of that, I will need to do a minus, right? And then I have sigma z. And again, I need to multiply this by the area of the boom, which is BR. Is correct? And then I will have a force if I do that. So this is a contribution from the direct stresses. But I have also the shear flows. I need to include the contribution of the shear flow. So I will continue here. So plus, I will continue here below. Okay, plus. Let's now add the contribution of the shear flows. Let's start with this one here. Okay, this shear flow. So QR. So this is a shear flow, which, don't forget, is a force per unit length. So I need to multiply this QR by dz, right? And then I will have a force. And now this one. So it's going to be opposite to my z-axis, so that's why it's minus. QR minus 1, again, times dz. And that's all I have. And this needs to be equal to 0 to be in equilibrium, isn't it?
Doesn't sigma z cancel?
They cancel now, yes. So many things, not many things. This guy will cancel with the sigma z, right? You agree?
Yeah.
So, yeah, it's true, right? So at the end, we will have delta sigma z BR. So let's do it here. We will have, if you continue here, we will have delta sigma z BR plus QR delta z minus QR minus 1 delta z. And this needs to be equal to 0, isn't it? Is this correct or not? So this is the equation we obtained from the equilibrium of the boom. And basically, what this equation is saying, don't forget we are looking for, imagine we know the shear flow in the skin QR minus 1. We want to know the shear flow in skin QR. So if we know the variation of the direct stress sigma z, we can then find the variation in the shear flow, right? The good news is that, well, I can say that this variation, I can say that the variation on the direct stress is going to be equal to the derivative of the direct stress in order to my z coordinate times delta z, right? A linear approximation. This comes from the Taylor series, right? You know this Taylor series, right? So we can say that the variation on the direct stress will be equal to the derivative of the direct stress in order to z coordinate times a delta z, or an increment in the z coordinate. And why am I doing this? Because I know that the direct stress sigma z, it comes from the bending, right? The direct stress comes from bending, and we know from bending, our equation from bending is, I will try to write it here. We have the bending moment in the y direction times the second moment of area about the x-axis minus the bending moment in the x direction times the product of inertia dividing by ixx iyy minus ixy square. This will multiply the distance to the neutral axis in the x direction, plus, I will continue here below, plus, now we have another term, which is, so the denominator is the same as the other one. This is from unsymmetric bending, okay? And then we will have here mx, second moment of area, and my, product of inertia. And this will multiply the coordinate y, which is the distance in the y direction to the neutral axis. This is the equation for unsymmetric bending, is the general bending equation, where these mx and my are the bending moments, and then from this equation we can get the direct stress from bending, right? We didn't talk about bending here, but I assume that you did this in year 2. So, and now look at this. Now what I really want is the derivative of this direct stress. So I just need to make the derivative of this direct stress is going to be equal to the derivative of my derivative of mx here again derivative of mx and the last one is the derivative of my. Okay. Yes, that's all we need. And now I know that there's one more thing I know, that the transverse shear force Sx is going to be equal to the derivative of the bending moment, and the transverse force Sy is going to be equal to the derivative of this bending moment. So I can just replace this in this equation, and I will obtain here Sx I will obtain here Sy, right? Sy here, and Sx in this last one. Okay? Are you following? Sorry? More or less? Basically, I'm just using the equation from asymmetric bending for direct stress, and I'm making the derivative now. That's it. Nothing more than that. And what I'm going to do now is replace this one here, right? And then once I replace this one here, I can replace this one here, and I will get something at the end. That's what I'm going to do now. So I can say, if I multiply now this by delta z, so if I multiply the left-hand side by delta z, I need to multiply this one here by delta z, and this one here by delta z. Right? You agree with me? And then, yes, I can, this is going to be my delta sigma z, my variation on the direct stress that I need to include in this equation here at the top. Or if you want, because this big equation, I don't want to write it again. So what I'm going to do is I'm going to multiply this delta sigma z, which is this equation, by the area of the boom. I'm going to do it now here. So I'm going to multiply this term by BR, and this term also by BR. So what we will get here is going to be times BR, right? And then I can then say that so this term here, so I'm going to do this way. This term here is going to be my delta sigma z times BR, right? Is going to be equal to this term. If I add now this and these terms here, so if I continue this and add plus KR delta Z minus KR minus 1 delta Z, which are these two terms here. I know by doing that, I know that this, all of this needs to be equal to 0, right? You agree with me? Because that's what I have here in this equation, equal to 0, right? Okay? And why is this? So we arrive at this final. I'm going to delete this just. So look at this now. I can cancel this delta z. It appears here everywhere, right? I can cancel this delta z. And then at the end, what I have is I can send these guys to the left-hand side and change the signal, or I can do it in the other way. I can send this to the left-hand side and change the signal. And then if I do that, I will get something like this. I will get here minus. And this one now here is going to be minus. And this term here is going to be equal. Right? I can delete this delta z. Okay. I can move this guy a little bit closer to this. Can move this guy a little bit closer to this. Almost there. Look at this now. This term so I'm continuing the equation here, right? So this term is what? QR minus 1 is my variation in my shear flow, delta Q, when I cross the boom. Don't forget, our original goal, if we go back some slides, if we go back to this slide, my original goal is I wanted to know the variation in my shear flow when I cross that boom, BR, right? So the variation of my shear flow when I cross the boom is QR minus 1. And that variation is given by what I have here on the left-hand side of this equation. So when I cross the boom, the variation on the shear flow is given by this, what I have here on the left-hand side. And we know everything we have on the left-hand side. Because what you have on the left-hand side is, you have the transverse shear forces, Sx, Sy. We know that. That is given in our problem, is the lift, for example, in a wing. What else do I need to know? I need to know the inertia properties, Ixx, Iyy, Ixy, products of inertia, second moments of area. So I know that. That is the characteristic of my cross-section. What else do I need to know? I need to know the area of the boom that I am crossing, BR. I know which boom I'm crossing. So it means I know BR. I know the area of the boom. And the other thing I need to know is the distance to the neutral axis of that boom. I know where that boom is. I know the distance x and y to the neutral axis. So I know everything. When I'm crossing that boom, I know everything on the left-hand side of this equation. And then I can calculate the variation on the shear flow, right? So this is one thing. One very important conclusion that we are going to use a lot, solving examples with this equation. The other thing is that we can have, for example, a boom like this, and we can have many skins coming to this boom. I can have, for example, a shear flow, this one going this direction. I can have a shear flow going this direction. So this is boom 1, this is boom 4, this is boom 3. I can have a shear flow going into the boom, Q3. I can have a shear flow here, Q2, also going into the boom. I can have all of this very generic thing. So when I am crossing, so this is going to be my boom R, the boom that I am doing the analysis, the boom that I am crossing, okay? So look at this figure here. In this example, the flow QR is leaving my boom BR, and the flow QR minus 1 is crossing, is arriving at boom BR, right? And if you look at our final equation we obtained, the shear flow that is leaving is positive. The shear flow that is arriving is negative, affected by this minus thing. So, why am I doing this? Because in this generic example, I can say shear flows leaving boom R are going to be positive. So in this case, we will have shear flow leaving is shear flow Q1, shear flow Q4, right? This shear flow here and this shear flow, they are leaving boom R. So I consider them to be positive. And shear flows Q2 and Q3, they are arriving at the boom. So I need to make them negative. Okay? So this is this right-hand side of this equation. Now I need to get all of this left-hand side of this equation. I'm just going to copy it. So all of this left-hand side, I need to paste it here. And then I need to say, this is going to be equal. Okay? So look at this. When I cross boom R, this is going to give me the balance or the variation of the shear flow, the total balance of the variation of the shear flow. And that variation needs to be equal to what I have here on the right-hand side. And I know everything because this x, y, br is the area and the coordinates, the distance to the neutral axis of the boom that I am crossing or doing the analysis, okay? I think the best way for us to get this clear is, so I just wanted in this first half of the lecture today to derive this very important equation for the idealized structures. And now in the second half, I propose let's apply this in one or two practical examples, okay? Then you can see how easy this is going to be when compared with transverse shear flow we did 2 weeks ago, okay? All right? No questions? I'm a bit concerned. When you don't have questions, you understood 100%? Or you just didn't understand anything? I hope it's the first one. So let's see in the second half. Let's do a 5 minutes break then, okay? Okay, so let's start with this example. Open cross section. So you will have this example in your notes. You don't need to copy this now. You will have this in your notes, detailed example. You will have as well in this video I'm doing. So please pay attention. Try to follow. If you're not following, ask me to stop. So I just prepared. I just wrote here the general equation for the shear flow. So basically, when you cross a boom R, you can see here BR. So we are crossing a generic boom BR. Okay? This is the x and y distance of this boom BR to the neutral axis. And this is the shear flow before crossing the boom, in the skin just before. And this is the shear flow after crossing the boom. Yes?
Should that be SXX or just SX in the first line?
Oh, yeah. Yeah, it's SX. So this SX, this guy here, should be SX. Oop. Right? Again. Yeah. This Sx, so don't forget, this Sx and Sy, they are the transverse shear force. Okay? In the x and y direction, of course. So in this example, this is going to be our Sy, 48 kilonewtons is the transverse shear force. And Sx equal to 0. We don't have any transverse shear force in the x direction. So this is, don't forget, this is a cross section, okay? We are analyzing a cross section. Okay? All right. So, in this example, you have 4 booms. All these booms have the same area, 300 millimeters square. And what I want to know is basically the shear that is flowing in these cross sections, right? So the first thing we should do is we should draw an initial orientation for the shear flows. Okay? So let's say between boom 1 and boom 2, I will have a skin, and I'm going to say I will have a shear flow here that I'm going to say is my shear flow Q1. Okay? And then this will continue to flow. I will then cross my boom number 2. And then after crossing boom number 2, I will have a shear that will flow in this direction. And this shear I'm going to say is Q2. It is going to be constant in this skin between boom 2 and boom 3, but this Q2 is going to be different from Q1 because I crossed the boom. Okay? And then when I continue, the shear will continue to flow, and then it will go on this skin here, and then this shear is going to be my Q3. All right? So that's the first thing we have to do. We just assign an initial orientation for the shear flows. In this case, I assign the anti-clockwise orientation, but you can assign, because you need to imagine this like a flow. We are going to see in more advanced cross sections, like if we have multiple cells in our cross section, you can imagine this shear like water flowing in pipes, in tubes, okay? And then part of the water goes in this direction, part goes into another direction. We are going to see that. But in this case, it's very clear. The shear will start flowing from boom 1, and then it will go all the way in the anti-clockwise direction until it arrives at boom number 4. Okay? So this is one first thing that you have to do. Second thing that you need to consider is the shear flow before crossing the boom. This QR minus 1. Open cross sections is very easy because we start our analysis. In this case, we will start our analysis saying, okay, I'm going to see what is going to happen when I cross my boom number 1, which is located at this free edge of my cross section. And I know that before I cross this boom, this shear flow here, I can call it Q0, is going to be equal to 0. There's no shear flow there, there's no material there, right? So the shear flow is 0. So if I start my analysis saying I'm going to cross boom number 1, then I can say this QR minus 1 is going to be equal to 0. This guy here is going to be equal to 0, right? We will then see how we do this with closed cross sections. But let's focus now on this example. Other thing I need to do before I start this analysis is I need to look at the inertia cross-sectional properties, second moments of area, and products of inertia. And the first question that arises is, how do I calculate, for example, how do I calculate this second moment of area for example, IXX. If I have an idealized structure like this with booms, don't forget, we are assuming the skins, they have 0 thickness, right? So everything is concentrated on the booms, right? So how do I calculate, in an idealized cross-section, how do I calculate the second moment of area about the x-axis? So I need to do a summation from I equal to 1 to n, where n is the number of booms that I have. In this case, I have 4 booms, right? And I need to do a summation of the area of the boom, bi, times the square of the distance of each boom to the neutral axis. This comes from the parallel axis theorem. Remember? This comes from, I don't know if you remember, if you have, for example, imagine you have this rectangular cross-section here, where you know that about this x bar axis, if you calculate your second moment of area about this x bar axis, you will have, so let's put some dimensions here. So let's say this is the width b, this is the thickness t, okay? This second moment of area about this axis is bt power 3 over 12. Remember this equation? Now imagine I want to get the second moment of area about the parallel axis, x. And let's say this distance between these two parallel axes, from here to here, let's say this is equal to d. So how can I obtain then my second moment of area about this x-axis? The parallel axis theorem, this is equal to this x bar, which is this bt cube over 12, plus the area of my rectangle, which is b times t, so this is basically the area, a, times the square of the distance between these two parallel axes. Remember this? I remember we talked about this in year 1. I clearly remember that. So this is exactly this. We are applying this to the booms. We are applying this bit. If you look closely, this is the area. This bi is the area of the boom. And this is the square of the distance to the neutral axis, right? So basically what we assume here in the boom is that the area is lumped on the boom. And then we just need to, if I want for them to calculate the contribution for the second moment of area of this boom number 1, I just need to multiply the area of this boom with the distance of the boom to the neutral axis. Square of the distance to the neutral axis. Okay? So in this case I have 4 booms. So it means I know the area of, so let's start with boom number 1. The area is 300. The distance is 2000. So 2000 square. Boom 2 also has area of 300. The distance is also 2000 to the neutral axis. Boom 3, the area is also 300. The distance is minus 2000, but because you have square, it doesn't make any difference. Same thing for boom number 4. So I can just multiply this by 4. And this is the second moment of area. Isn't this easy? Huh? Always like this. So can you give me, we need this final number. Can you do this maths, this calculation for me, please? Give me the final number. We can put it here. We need to find space. 4 point?
8 times 10 to the 9.
Millimeters power 4, right? This is the second moment of area, IXX. What about the second moment of area about the y-axis? Do I need to calculate that? This is something that you need to... Let's do some analysis on this equation here, okay? So I'm going to copy this equation again. Copy and paste. And then let's see what is happening with this equation. So, first, do I have this Sx, transverse shear force? No, this is equal to 0, right? You agree with me? So I can just delete this contribution. Let's do that. I can delete this is 0, Sx is 0. Sorry. Before we talk about Sx, sorry. Let's first focus on this product of inertia, okay? That we have here, here, and here, okay? Product of inertia. This is a symmetric cross-section. You agree with me? What is the product of inertia in a symmetric cross-section? 0, right? So this term is all 0. So I'm going to start with this one. I'm going to delete this term as well. Product of inertia is 0. Okay? Same thing here. I'm going to delete this term, product of inertia is 0. And this term here below, product of inertia is also 0. Okay? Now, what else can I do? Look at this. I can cancel here my Ix, second moment of area about x-axis, and here I can cancel my second moment of area about y-axis. I can do this, right? So I'm going to delete. Going to delete this guy and this guy. Okay? And here I'm going to delete this and this. Right? Now we can look to the transverse shear forces. I only have this transverse shear force, which is my Sy, is my transverse shear force in the y direction. You agree with me? So Sx is equal to 0. So this term is going to be equal to 0. So it means I can, if this term is 0, all of this term is going to go away. You agree? This is the part I like most. Right? Much easier, right? So, from symmetry and from the transverse shear force, we could simplify the general equation into a much simple one that we will use in our analysis here. And now we know everything in this equation, right? We know. We can continue here. We know this is going to be equal to QR minus 1 minus, look at this, transverse shear force is 48 kilonewtons. I can convert to newtons, so we'll have 48,000 newtons. The second moment of area we calculated before is 4.8 times 10 power 9. Oh, it's a very nice number. 4.8 times 10 power 9, right? This is our second moment of area about x-axis. The boom area, so is 300, but it's better to leave it this way because in this example it all is 300, but in different examples they might have different areas. and then distance to neutral axis of the boom. So we will focus on this equation now. Okay? And then what we are going to do now, we are going to start crossing the booms. This is how it's going to work. This idealized structures is crossing booms. That's it. Starting with boom number 1. So what you can do is, let me copy this now. Let me just copy this. Paste. Okay. So let me just put this one here again. Q1, Q2, Q3. Okay. And let me copy now this final equation as well. Is the equation we are going to use. Copy. And paste here. So this is going to be equal to QR. Okay, so perfect. We have our shear flows, how they flow in our cross section. We have the equation that will allow us to obtain the shear flow after crossing a boom, and then we do something like this. Crossing. I'm going to write it here. Crossing boom number 1. You do this way. So I'm going to start the analysis by crossing boom number 1. And we are going to write this equation. Use this equation. So this QR, when I cross boom number 1, this QR is going to be equal to my shear flow leaving the boom number 1, which is Q1. QR minus 1 is the shear flow before crossing boom number 1, which is 0. Minus. Now we have 4.8 times 10 power 4. So we will have minus 5. What do you think about this? Yeah. Is this correct? Now I need to multiply this by the area of the boom that I am crossing, which is boom number 1, and the area is 300. And I need to multiply now by this y is the distance of boom 1 to the neutral axis, which is 2000, right? So if you do these calculations, you will have 6 times 10 power nothing. You have 6, isn't it? Huh? Newtons per millimeter. You agree with me? Isn't it? Minus, of course. I just wanted to check if you were paying attention. No, I'm lying. It was my mistake. Minus 6. So this minus 6 tells me what? What do you think? We obtained Q1, the shear flow that is going from boom 1 to boom 2. We obtained the value of minus 6. This means that, in fact, the shear flow is not going from boom 1 to boom 2, but is going from boom 2 to boom 1. Right? That's what this minus means. So anyway, we have Q1. So what do I have to do next? I need to crossing now the next boom, which is boom number 2. I'm going now to cross boom number 2. I'm going to use the same equation to cross boom number 2. So when I cross boom number 2, this QR is equal to what? Is equal to Q1 or Q2? Which is the shear flow leaving boom that I'm crossing. Leaving the boom I am crossing. It's Q2, right? So this QR minus 1 is the shear flow that is arriving to the boom that I am crossing, which is Q1. And then this term is same, minus 10 power minus 5. The area of boom 2 is also 300. The distance of boom 2 to the neutral axis is again 2000. So I know how much is Q1 is minus 6. You agree with me? So I can replace Q1 by minus 6. And this is going to be minus 6 again. So at the end I will get minus 12 Newton per millimeter. Right?
Yep.
And now what I have to do is, the last step is crossing boom number 3. So the shear flow leaving boom 3 is Q3. The shear flow arriving at boom 3 is Q2. So that's what I have to do. So I will have Q3 is the shear flow leaving, is going to be equal to the shear flow arriving, which is Q2, minus the same thing, minus 5 times 300 times. What is the distance of boom 3 to the neutral axis? Minus. This is very important. Don't forget this distance neutral axis comes from the bending thing, and then in bending is very different if you have something above neutral axis or below, right? It's the difference between tensile stresses or compressive stresses, right? So the signal here is very important. So we need to put here minus 2000. Okay? So if you replace Q2, it was minus 12. Minus with minus will be plus. Plus 6 here, you'll get minus 12. Minus 6. Right? And now, what I'm going to... So we have the shear flows. What I'm going to do now is... They all are negative, right? Minus 6, minus 12, minus 6. So I'm going to reverse my initial orientation. So they flow not in this anti-clockwise, but they will flow in the clockwise direction. So what I have to do is, basically the shear flows, they will come from boom number 4 and will flow in this direction. So this is 6, this is 12, this is 6. Okay? And so we have the shear flows. The analysis is done for the shear flows. But there's one thing you can do to make sure you have everything right, which is, let's look now at this final cross section, and let's look what we have. So I'm going to use the green color here, in this small space here. I'm going to check with you the summation of forces in the x direction. Needs to be equal to 0 in this case, because we don't have any transverse shear force Sx in the horizontal direction, right? So what do I have? If I look at this one, first, I have 6, which is the shear flow. So this is a shear flow. I need to multiply this shear flow by the length, which is 2000. Then this will give me the force in this skin, right? But I have something more in the horizontal direction. I also have this skin. The shear flow in this skin here in the bottom will also produce a force in the x direction, but now this force is opposite to x, and the shear flow is 6 again, and I need to multiply again by 2000. So the result of this is equal to 0, isn't it? Yes?
Sorry, I've got a question about the distance to the neutral axis. Going back to your equations.
Yep.
You've got Q1, you've got the y distance is 2000.
Yep.
Q2.
Yep.
And you've also got 2000.
Yeah.
1,000.
Sorry?
Is the distance on Q2 is it not 1,000?
No. So the neutral axis is this one, right? You want the distance of this boom to the neutral axis. So you want the distance in the y direction. Don't forget here, you have the distance in the y direction, okay? Is the y component of the distance. Okay? So, we have summation of forces in the x direction equal to 0, which is correct. I don't have any external force in the x direction in my cross-section. But what is happening in the vertical direction? Summation of forces in the vertical direction, they need to be equal to 48 kilonewtons. Don't forget, shear flows, they are internal forces per unit length. The internal forces, they need to be equal to the external forces. Let's see if we have a total of 48 kilonewtons in the vertical direction. Look at this. What is the shear flow, the only shear flow that we have in the vertical direction? Is this one in this skin, right? You agree with me? So if I put it here, I will have shear flow is 12 newtons per millimeter, but I need to multiply this 12 by the length of my wall to 3, which is 4,000. This is equal to what? 48,000, right? Newtons, which is 48 kilonewtons, right? So, this internal shear flow, when I multiply this 12 by the length of my wall, I will get a total force which is equal to my external force on cross-section. If you got it different, it means you have something wrong. Okay? So it's a good way to check that everything is right. All right, so I think if we do one more example, it might not be very productive. That's my feeling. I'm reading your faces. Okay, we have the plan we have for the lectures. Like I told you, we have to do something more on thin-walled idealized structures because we have to deal with closed cross sections and also multicellular cross sections. For example, imagine you have a cross section with two cells, like this. You have booms here, but you have two cells. In a wing is very typical, right? You can have airfoil in a wing. You can have one spar here, another spar here. So you can have three cells. So we have to do this kind of problems, okay? So that's what I propose to do next week. These multiple cell problems in idealized structures. And then after that next week, so in 2 weeks' time, we can start fatigue. Okay? Yeah.
If you want to try questions, someone behind.
If you want to try, yeah, it's a good thing. If you want to try these questions, in these notes I'm going to upload, there are some examples, not many, but some examples. But I strongly recommend, I'm going to write here, okay? This book, Aircraft Structures for Engineering Students. This book, with this title, the author is T.H. Maxson. Is an amazing book for this kind of problems, okay? You can find, this will be in the I'm recording this will be available to you. Another book you can look to is, I don't know the title very well, but I know the author, which is Curtis. Maybe the book is Aircraft Structure, something like that. This is the author, Curtis. You can find these two books in the library. There are many different copies of this book in the library. So if you want to start practicing these kind of things, you can look at these books. They have many examples there, detailed solutions, proposed examples. I also will upload these notes in Blackboard with some more examples here. But what you can do is, we'll discuss next week, okay?